There's maybe one thing that's new to you from Algebra 2 today, but a lot of what we talk about is something that you have seen before. Although this is the last chapter of Algebra 2, so sometimes it doesn't stick with us as much as some other chapters. Whenever I introduce rational functions, I always ask, what math word is in the word rational? Ratio. Okay. And what is a ratio, or what does a ratio look like? A fraction. Excellent. So rational functions are really functions that are fractions. Okay. Here's the mathematical definition for a rational function. Is everything okay, James? A rational function is a quotient. So that implies division, which fraction is just division, of polynomial functions. And in the mathematical definition, I name them n of x and d of x, representing numerator and denominator. Okay, so I'll use that notation later on to refer to numerator and to denominator. Such that d of x is not equal to 0. Why do we say that d of x is not equal to 0? You can't have zeros in the denominator, you'll get an error, it is undefined, so we're just saying like, hey, you're going to have a polynomial down there, but that polynomial can't equal 0. That's trouble for us. When the denominator equals 0, you have a restriction to your domain. And we saw this happen in chapter 1 when we did inverse functions. Right? Determine the domain of a rational function. Whatever made the denominator equal 0 was restricted, not included in our domain. Now, a big difference moving into chapter 2 is some of our rational functions will look different. I could have a quadratic in the denominator now. Before they were always linear in chapter 1. And if a quadratic is in my denominator, it's possible that there are 2 values that make my denominator equal 0. So not only would I have to exclude one of those, but I would have to exclude 2 numbers from my domain. Every time you exclude an additional number from domain or range, you have to add a new set of intervals, right? So if we only exclude one number, we have 2 intervals. If we're excluding 2 numbers, then we would have 3 intervals. So the left to the right and in the middle. There is something that we will look for in our rational functions, a characteristic of the graph, and it's called a hole. A hole is literally like a point that should be there but isn't. It makes your graph discontinuous.
So is it kind of like an imaginary? If it's like there but it's not there?
No, it's just a hole. There is no imaginary substitute for it. So it's not a placeholder, it's just a break. So how will we know there are holes? If n of x and d of x, remember those just mean numerator and denominator, share common factors, there is a hole in the graph at the 0 of that common factor. So if you discover that the numerator and the denominator share a factor of x plus 5. You're going to cross out that x plus 5. There's a hole at x equals negative 5. It's a 0 of that factor. A hole in your graph is going to be represented by an open circle or open dot. So it literally is just like a point that isn't there. And since it's a point, it needs to be an ordered pair, so it has to have an x and it has to have a y. You can find the x by looking at the 0 of the common factor. To find your y, you'll plug that x into your reduced function and evaluate for y. So we'll do an example. You'll see this happen. But you just plug your x back into your reduced function. You don't want to put it back into the original function because then you'll get 0 over 0. And 0 over 0 is really big trouble because is it 0 or is it undefined? We don't know. So we have a special name for that. We call it indeterminate. Can't say anything at all about it. So you got to plug it into the reduced function. Okay? How many people think they have talked about holes before in Algebra 2? You remember this? A handful. Okay. Some of us may have had it as a side discussion and others not. In addition to holes, this should sound more familiar. You're going to have possibly vertical and horizontal asymptotes. So vertical asymptotes we already kind of know about because of Chapter 1. They're going to be places where our denominator equals 0. The only difference here would be if one of the factors was a hole, the hole takes precedence. It's a hole, not a vertical asymptote. So I always check for holes first. What's left over could be a vertical asymptote. So you just set d of x equal to 0. To do the horizontal asymptote, you have to consider the degrees of the numerator and the denominator. And what do we mean when we say degree again? The highest exponent. Okay, so you're going to be looking at the highest exponent of the polynomial. When you're comparing two numbers, there's really three things that can happen. It can be equal, one can be less than, one can be greater than. Okay? So as you compare your degrees, if the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is at y equals 0. If the degree of the numerator is equal to the degree of the denominator, your horizontal asymptote is at y equals a over c. Where a over c is the ratio of LCs. What do I mean when I write LCs? What's an LC in a polynomial? Leading coefficients. Write that down if you don't know what LC is in your note. A leading coefficient. So you're comparing the degrees, the highest exponent, and when they're the same, your horizontal asymptote is the ratio of the leading coefficients, the numbers in front of those terms with the highest exponent. And finally, if the degree of the numerator is greater than the degree of the denominator, there will be no horizontal asymptote. It does not exist. I use the abbreviation DNE. You can say none or DNE doesn't exist, whatever you want. Just don't put 0. That's confusing. Now, today we're going to be focused on number 1 and number 2. What if it's less than, what if it's equal? Tomorrow, we're going to do an additional set of notes for a special case of number 3. Now, there's one final thing on this slide, and I just want to put this out there in case you encounter a problem like this. Because this can happen as the rational functions, the fractions, and the polynomials, the numerator and the denominator become more complex, you actually can cross a horizontal asymptote. It just happens in the middle of your graph. The horizontal asymptote is really for like end behavior. So remember, end behavior is far left, far right. So it is possible to cross a horizontal asymptote. Don't be super alarmed if your ordered pairs are telling you that that's happening. At some point, it'll go back towards the horizontal asymptote. That's very uncommon, but I did want to put that out there. A couple other really quick things that you can find to help you get a better graph for a rational function would be intercepts. So you can find an x-intercept and a y-intercept. You guys should know this. You know, you completed the summer packet. To find a y-intercept, you're setting x equal to 0. To find an x-intercept, you're setting y equal to 0. I do have a shortcut for rational functions that I think about for x-intercepts. Remember that rational function f of x is n of x over d of x. And if we were to set f of x equal to 0, we're saying that that fraction is equal to 0. So if you have a fraction equal to 0, what do you know about either the numerator or the denominator? What must be true? You can't have the denominator equal to 0 because then that would be undefined, no solution. So what must be true if the fraction equals 0? The numerator is equal to 0. So in order for this fraction to be equal to 0, it must be 0 over something. Okay. So I have a shortcut that I use to check for x-intercepts, which is just set the numerator equal to 0. And that's based on my reasoning, what I know has to be true of a fraction so that it equals 0 for y. It must be a numerator. If you put in 0 and then solve any rational function, you're just going to multiply by d of x, and then it's going to disappear. I'm just getting rid of one step, really. Okay, so here are the things I'd like to see you guys doing as you're trying to graph. Okay. Number one, and this is going to be really important for those of us who haven't seen holes before, factor first. The only way you'll be able to see if you have a hole in your rational functions is if you factor to see if they share any common factors. If you don't factor those polynomials, it's not always apparent if they share a factor or not. So definitely factor. If you factor and nothing cancels, you can go back to the original and probably complete it like normal. But even factoring might be helpful for like finding the asymptotes and things like that. So always factor first and then do your check for common factors, which would give you a whole. After that, you're just kind of running through those other things. Vertical asymptote, horizontal asymptote, x-intercept, y-intercept. That's just going to help give you more understanding of what could be happening with this graph. After you've looked for holes, you found your asymptotes, you found your intercepts, then I would start sketching those things on the graph. When I do my example, I'm going to do it at the same time. So like if I find an asymptote, then I'm going to draw it right away. The last step I have, just to ensure that you have pretty nice graphs, get a few extra points if you need them. I'll generally say, like, think about your graph as being split up by vertical asymptotes. Have at least 2 or 3 points on either side of the vertical asymptote. That'll just ensure you've got a pretty accurate graph in the right location. Now, for these final steps, it is okay for you to use the simplified function if you found a hole and you crossed off some factors. You can use the simplified function. That might make it a little bit easier, smaller numbers, less computation. Okay, so you can use the remaining, or what I might call the leftover factors, to do that other stuff. Okay, let's look at a couple of examples. Okay, we're going to start real nice and easy. Warm up to one that is a little more complicated. F of x equals 3 over x plus 4. Real easy to write down too. F of x equals 3 over x plus 4. Okay, now you're in the pre-calculus mindset. The first thing you're going to do is check for holes, which means you got to factor if possible. Can you factor anything in this problem? No, it's pretty much already factored. So that makes it pretty simple. So there is no hole, I don't have to worry about it. Move on. Vertical asymptote. Vertical asymptote, values that make the denominator equal 0. So x plus 4 equals 0, x equals negative 4. The asymptote should always be written as equations of lines. I'll go over here to my graph, and then I'll plot that vertical asymptote at x equals negative 4. Cool. Horizontal asymptote. Compare the degree of my numerator and my denominator. So I'm looking, are they the same? Is the numerator less than? Is the numerator greater than? You want to say what, John? What is the highest exponent in the numerator? 0. So you're looking for the x variable. Is there an x in the numerator? No, so it must have been x to the 0. What's the degree in the denominator? 1. Is this linear?
Why is that 0, not 1? Because you take 3 to the...
3 to the first is 1. Yes, that's true. Yeah, you're looking at the degree of the variable. And there is no variable.
So I'm asking if there's no x in the numerator, it's always d is 3.
Pretty much, yeah. Right? If there is a variable missing, the degree is 0. It's constant. Okay. So we would say the degree of the numerator is less than the degree of the denominator. That's a good one for us to look at. What is our horizontal asymptote then? Y equals 0. And that would be my x-axis. Now I'm going to mark mine just like right underneath that line so you can see where I'm putting my asymptote, but I mean it to be the actual x-axis. Okay, find a y-intercept if you can. Y-intercept, you're plugging 0 in for x. When I do that, I just get 3 over 4. So I can plot that point up 3/4. For the x-intercept, remember my shortcut, because it's a fraction, my numerator would have to equal 0. So I would set 3 equal to 0. How do you feel about that? 3 equals 0. That is not true. You feel pretty bad about that. So that means there is no x-intercept. So when things like that happen, it just means like, okay, you can't find an x-intercept, move on. And that makes sense because your horizontal asymptote is at equals 0. Okay, so I have 2 asymptotes and a point. I probably need some additional points. Make the little table of values over here. You can choose any x's that you want. If I'm graphing over here on the right side of my vertical asymptote, I might choose -3. I might choose 2. It doesn't matter what x's you pick. You try and get some extra points. Plug those numbers in. to your f of x for x, you're going to come up with 3 and 3/6 or 1/2. And then you can plot those points. So negative 3, 3, 2, 1/2. You okay with how I got my y values there? So I'm feeling a little bit better about what's probably happening with this graph. I've got some kind of turn happening, bend right here, and then I must be approaching my asymptotes. I'm kind of trapped in that little section. There is no x-intercept. I set my numerator equal to 0, that's why I have 3 equals 0 up there. But how do you feel about 3 equals 0? True?
Oh, you said top equals 0.
That's my shortcut. Yeah. Okay, now I need to figure out what's happening on the other side, so I might choose like -5 and -6. Notice I'm not going to put in -4 because that would give me undefined. So there is no point at -4. That gives me -3 and -3/2. So I can plot those points. And I think I know what's happening over there too. If you're not sure, you just keep plotting a few more points. And maybe like spread out your points so you can see, okay, what's happening a little further down, what's happening a little bit closer. Figure out what's going on there. Are there any other questions about that I can answer for you? Does that picture look familiar to you? In Algebra 2, you might have named it. That's called a hyperbola. They're called 2 branches. So a lot of times the rational functions come like that. They don't have to. Rational functions can look all sorts of ways. There can even be 3 pieces of a graph if you have multiple asymptotes. Now, let's do one that has a hole. Yes. Let's do one with a hole. F of x equals x squared minus 4 over x squared minus x squared. Yep. It'll give you a rational function and then read the directions. It'll probably tell you like hit the domain, find the vertical asymptote, find the intercept. It'll give you some directions. But these are kind of like my expectations, what I would expect you to do on a quiz or a test. Okay, so you are going to tell me to do what first? Factor. Can anybody factor my numerator? X plus 2, x minus 2. Excellent. What about my denominator? X minus 3, x plus 2. Okay, so the x plus 2's cancel, which that immediately tells you you have a hole. Okay, you have a hole at the 0 of that factor. So the hole is at x equals -2. Okay?
So how would that look on the graph?
Yes, how would that look on the graph? When I say that you have a hole at x equals -2, we know the x coordinate for a hole, but we really need to also figure out the y coordinate. Because remember, the hole is just like a point that doesn't work.
Oh, that's just one point.
Yeah, it's not like an
So
asymptote.
what happens like with the line?
I'll show you. So we need to find the y coordinate for our hole. You're just going to take this value, -2, and you're going to plug it into any factors that are left over. So y equals -2 minus 2 over -2 minus 3. That's -4 over -5, which turns into a positive 4/5. Don't be alarmed, like when you're doing your table of values, or you're finding the y coordinate in your hole. You're going to get a lot of fraction y coordinates because you're working with a fraction function. So that's normal. And then on my picture, I go -2 to the left, up 4/5, so not quite all the way to 1. Now just draw an open circle for now. It's just a point. I'll be able to use that point as like one of the points to make the graph. I just won't draw a line through it. I'll go right up to it and then start right after it.
So you have more than one hole.
You could if more than one factor counts home. Most likely you'll have one hole. Can't.
Like the -2
The -2, so you said x plus 2 cancels the 0 of that factor. So if you set x plus 2 equal to 0, the solution is -2. That's why we know the x coordinate of our hole is -2.
Okay, and then why did you subtract 2 from that?
Because then to get your y coordinate, you gotta plug it back into what's left over. So I put -2 minus 2, -2 minus 3.
Oh,
Yeah. I don't want to plug it back into the original because that's when I get 0 over 0. Unhelpful. Good questions. Anything else? Okay, now I go along my merry way. Vertical asymptote, is there anything left over in the denominator?
Yes.
X minus 3, so that means I have a vertical asymptote at x equals 3. Horizontal asymptote. You can look at the reduced function, but I usually look at the original one because it's probably like written a little bit nicer. What do you notice about the degree of the numerator and the denominator? They're the same. So remember, when they're the same, your horizontal asymptote is at A over C, which is the ratio of your leading coefficient. So 1 over 1. So y equals 1. Let's see. I could do a y-intercept for an extra point. That's easy. If I plug 0 in for all these x's, they all come out to be 0. And I just have -4 over -6, which is positive 2/3. I can put a point right there. For an x-intercept, remember, I have a shortcut. Set my numerator equal to 0. Are there any factors left over? X minus 2. So that means that x equals 2, or 2 comma 0 is an x-intercept. So just by doing those, I have 3 points on the left side of my vertical asymptote. Do you kind of think you know what's happening with that graph? It probably looks like the other branch we had before. It just has a hole in it. That's what a hole in a graph is. It's different than an asymptote. You don't go to like positive or negative infinity around it. You just literally pick up your pencil and go on the other side. You still have to find the other piece, right? So maybe a table of values to find on the other side. That vertical asymptote was at x equals 3. So I might choose like 4 and 5. See what's happening over there? Now here's where your reduced function can be real handy. Instead of having to plug 4 and 5 into the original with all those x's, just plug it into the leftover factors. So 4 minus 2 and 4 minus 3 will give me 2 over 1. And then if I wanted to plug in 5, 5 minus 2 and 5 minus 3 will give me 3 over 2. So that's really handy to just use the reduced function. And I can plot those 4, 2, and 5, 3/2. So probably something like that. So your biggest issue that I want you to be thinking about tonight's homework is really like focusing on that factoring piece and making sure that you find your hole. I have one other thing that I'm going to say real quickly, and that's about domain and range, because the book might ask you to say domain and range. So if I were doing domain for this function, remember domain is all about what x's work. Where do you actually have a graph? From negative infinity until I get to my hole at negative 2. There is no graph there. So that's not part of my domain. It was one of those things that made my denominator equal 0. Negative 2. In union with, I'll pick up at negative 2, and then I can go all the way to 3. But that's a vertical asymptote, and there is no graph at 3. And then I gotta go to 3 to infinity. So when you have a hole and an asymptote, it's gonna mean that you're gonna have 3 separate intervals. If you do the range, you start at negative infinity, but now you're thinking about all the y stuff. When you get to your hole, instead of using negative 2, the x-coordinate, you put in 4/5, your y-coordinate. So negative infinity to 4/5, and union with 4/5 to 1, in union with 1 to infinity. So I have to exclude the hole from both, okay, x or y coordinates.